In this video, we will talk about water transport across the cell membrane. First, let's talk about the permeability of the membrane to water. The lipid bilayer has very limited permeability to water. To allow the rapid passage of water across the membrane, we have aquaporins. They allow free and continuous pathways for water molecules to move. Basically, they are just like water pipes in our home. Now let's talk about the force that drives the water movement. First of all, the water movement is always passive. To date, no water pump has been found on the membrane that can transport water actively against the osmotic gradient. So water transport across biological membranes is always passive. Okay, but what drives this passive movement? The answer is the concentration gradient. For example, let's say this container is filled exactly 1 liter on each side, and the membrane in between has only aquaporins and no other channels, so it's permeable to water only. Now, this solution has fewer solutes dissolved in it, and this solution has more solutes. Looking from the perspective of water, we can say that this side has more water concentration because it has more water, and this side has a low water concentration because it has less water in the same volume. Because of this concentration difference in water, the water molecules diffuse from the left side to the right side. Fundamentally, it is similar to the diffusion of solutes, but the diffusion of water has got a special name. It's called osmosis. Thus far, the discussion was neat and clean. But when studying physiology, there is a problem with working with water concentration. See, all the bodily solutions are very dilute, so they all have very high water concentrations, and it does not even change much. For example, let's say in this fluid we have 1 milligram of glucose in 1 kilogram of a total solution. Here, the concentration of glucose would be 1 milligram per kilogram of solution, and the concentration of water would be 999.999 grams per kilogram of solution. And here is a second solution with 2 milligrams of glucose in 1 kilogram of a total solution. Here, the concentration of glucose would be 2 milligrams per kilogram of solution, and the water concentration would be 999.998 grams per kilogram of solution. Now look at the percentage difference. 100% increase in glucose concentration is bringing about only a 0.0001% decrease in water concentration. This is because the solution is very dilute. For this reason, dealing with water concentration is not only cumbersome, but also imprecise. So in physiology, rather than looking from the viewpoint of water, we see from the viewpoint of solutes. Instead of calculating water concentration, we calculate the inverse of it, that is osmolarity. Osmolarity is basically the combined concentration of all solutes in the solution. As its inverse of water concentration, we automatically know that high osmolarity means less water concentration, and low osmolarity means high water concentration. We have already seen that water moves from high water concentration to low water concentration. Now, speaking in terms of osmolarity, we can also say that water moves from low osmolarity to high osmolarity. If all this is still confusing to you, simply remember that solutes attract water. So water moves where more solute particles are there. Now let's talk about osmotic pressure. Earlier we saw that in this container, the water moves from left to right by osmosis. Now, if we apply pressure on this side, this movement of water decreases. If we keep increasing pressure, the water flow can even reverse also. But the exact pressure where the flow stops is called osmotic pressure. Obviously, the more solutes in the solution, the more would be the pull on water, and therefore the more the pressure would be required to stop that flow, so more would be the osmotic pressure. Now, although this pushing part is important to understand the exact concept, I don't like it. I simply think of osmotic pressure as a magnetic attraction on water exerted by solutes. Next, the osmotic pressure is determined by the total number of all particles. It does not depend on the mass of the particle. that is, small and large particles, exert on average the same osmotic pressure. That is because the kinetic energy of a solute is equal to mv square divided by 2. Now in solution, large particles move at a slower velocity, so they have a larger value for mass, but a smaller value for velocity. And small particles move at higher velocities, so they have smaller m but larger v. When calculating kinetic energy using these values, we get the same average kinetic energy for all sizes. So they exert the same osmotic pressure. In a nutshell, the osmotic pressure is determined by the number of particles rather than the mass of the solute. Now before closing, let me tell you one bonus point. In solution, some particles interact with one another very strongly. For example, sodium and chloride ions. Such particles are attracted so closely that they behave as a single particle. Because of this, in body fluids, the actual osmotic pressure is about 93% of what you calculate based on concentrations of solute. That completes all the points that I wanted to discuss in this video. Now let's have a quick summary. The water molecules cross the membrane through aquaporins. It moves from high water concentration to low water concentration, or in other words, it moves from low osmolarity to high osmolarity. This is called osmosis. Osmotic pressure is a pull on surrounding water created by solutes in the solution. It's determined by the number of particles in the solution. That's it for this video. Click here to read the notes on this video at our website. You can also explore our entire physiology animation video library over there. To support my free content creation, first leave a nice comment and then share the video with all your friends and colleagues. Thanks for watching. See you in the next video.